All right. 3.5 is all about rational functions, and well, they're functions that involve fractions, and the fractions, usually what makes them rational, we should say this, means that within the fractions there are variables at the bottom. Now, this is really kind of like a brief flyover. There's so much we can talk about here, and so really we're brushing past, not brushing past, but we're flying over all of the concepts of rational functions. So we're going to be jumping around a lot topically. So this video definitely will be broken into chunks, or this section will be broken into chunked videos rather, because we got a lot to cover. First, what we're going to do is we're going to revisit the idea of domain. Now, first, it should be fairly easy to get through this section. There are a few things to consider, but we've already discussed a lot of the legwork, and you've already learned a lot of algebra techniques that would be needed. And remember that there's just one rule that we kind of, or rather, two rules that we worry about for domain, and it's is there a square root that can't have a negative, or is there a fraction that can't be zero in the denominator? And so right off the bat, we can actually see that, okay, well, I see definitely denominators, and let's see, can I make any of them zero? Well, we'll go in order. Careful, I'm going 1, 2, 3, 4. So for the first one, the domain would simply be x cannot be 12. Because look at it, plugging in 12 would make your denominator 0. Again, that's all we care about for rational functions. Can a fraction's denominator be 0? No. So then what can this domain be? Anything except plugging in 0 directly. Now remember that that's the easy way to say it, but then there's the interval notation way of saying I can go from negative infinity up to 12 without touching it, and then I can be anything right after 12 all the way to infinity. And I will just spoil it and say, and not spoil it, but I will say we will look at these graphs, and I think maybe this union symbol will click a lot more once we see what these graphs look like. The fact that they're in pieces in their interval might give you an indication as to what the graphs might look like. Okay, next question. You should be able to look at this one pretty quickly and determine the domain, because again, the domain is not anything to do with the whole structure. It's just, can I make my denominator 0? And you can, so that means your denominator can't be, or we can be anything except positive 5 or negative 8. Once again, remember we need to write that in interval notation, which would be I can be all the way negative infinity, and careful, think about the number line, until I get to negative 8. Then I'm fine after negative 8 until I get to 5. And then I can go from 5 onward and not worry about it. But again, we write our domain in least to greatest order, and we're saying I can't be two values this time based on my algebra and my denominator. Okay, now number 3 is a little bit interesting because if you try to factor this one, you're going to find that there are no factors of 9 that add to 0. So just to call back right a second ago, we did x squared minus 9. That definitely had factors that subtract to 0, 3 and negative 3, subtract or combine to make 0 in the middle. But there are no factors of 9 that add to make 0, because 1 and 9 make 10, and 3 and 3 make 6 if we're adding. So what do I do about this? Well, I guess I say it's not factorable, but does that mean that there's no way to make this 0? Not necessarily. It might mean that there are roots that are ugly and in a square root. And then the question is, does that square root have a positive or negative in it in the quadratic formula? And I don't feel like doing the quadratic formula here, so let me show you a really crazy idea for this particular question. If I just look at x squared plus 9, if I think about that, remember that x squared plus 9 is just a regular good old quadratic that's been shifted up 9 units. And so here's my question to you. Where does that denominator, where does this graph cross the x-axis or touch 0 for y? And the answer is nowhere. Very interesting. So this one's domain, catch this, is negative infinity to infinity, because x squared plus 9 will never be 0, because I can see its graph and see that it's always positive, and this is 9, by the way. Because what is this graph really? It's your regular parabola shape shifted up 9 units. And hopefully that example in itself is reason to kind of say, whoa, this whole course is, not always, but there are some pretty big ideas in this course, like function transformations, that just showed up here, and knowing what the parent graph looked like of x squared, and being able to kind of mentally reason with yourself that, okay, I only need to worry about this, right? X squared plus 9, treat it as its own little subproblem, and there we go. So the domain here is negative infinity to infinity, because there was no making this 0. To argue it verbally, which isn't mathematically rigorous. I mean, this is the proof right here that I can see the graph and see that it's always positive. But think about it. When we square something, what can you get out of a squared? If I plug in 0, I get 0 squared, and then plus 9, so I'm at 9. There I am on the graph. If I plug in 1, then I'm 1 squared plus 9, which is 10, so I'm a little higher up. If I plug in negative 1, careful, that still ends up being positive 1, after I square it, and then plus 9 gets me 10. And so that's just a very quick way of saying the lowest value I get is 9. Anything else I plug in here, positive or negative, will square and add to 9 and become only more positive. So there's no making that denominator 0. Hopefully you kind of catch that argument, or hopefully this graph explains why in this one, even though there is algebra on the bottom, because this algebra on the bottom could never be 0, there's nothing affecting your domain. Very interesting. All right, now for the last question, this is another important factoring technique that we've already seen in the last video for this module, and so I'm going to cut right to the answer that my full domain is from negative infinity to negative 6, then from negative 6 to positive 6, and then from 6 to infinity. And if you're sitting there going, how on earth did he do that? Then I need you to remember and memorize that that was a difference of squares, and so that's what it factored down to. And you can see that negative 6 and 6, as you would plug them in this order, are the things that must be excluded, because that's what this breaks down to. So never forget factoring of your differences of squares. Also, never forget regular factoring and by grouping. Thankfully, I didn't put a regular trinomial in there, but I might later in the section. Okay, up next, don't be scared, but here are what some rational functions look like. And right here, these vertical lines actually have a name. They're called vertical asymptotes. Now, there are many ways to describe what an asymptote is. One way I would verbally say it is that an asymptote is an invisible line, but see, we're drawing it with dashes. It's an invisible line that your graph is not allowed to cross. However, that's not a totally rigorous definition, because you can see it does cross through this horizontal asymptote right here. But a vertical asymptote is more so, uh, I mean, yeah, something your graph isn't allowed to cross, or it's a break in the domain, but more so it's the fact that at an asymptote, look at what happens. These graphs either shoot upwards forever or shoot downwards forever, depending on how you want to state that. Now, with that being said, we're going to look at some funky notation, but we're essentially going to be answering some questions about asymptotes and end behavior in this next section. So what on earth is going on here? First thing we're going to do for this number 1 is we're going to translate this into words. And we're going to kind of use just that little bit of space we have above that question 1. So what we're going to say is, what this is saying is, as x approaches, that's what that arrow means, 3 from the right, and that's all we'll write there. So as x approaches 3 from the right. So take a look at this crazy wild graph and go ahead and find x equals 3. Hopefully, you started on the origin and you went right 1, 2, 3. Here is my vertical asymptote, x equals 3. Now, then it says, what happens as we approach 3 from the right? What does that mean? Well, there's a left side of 3 and there's a right side of 3. And what we mean as I approach 3 from the right is it means go to the right, look at this segment, and now go backwards but follow the graph. So hopefully you see what I mean by that. Here's x equals 3. This is my vertical asymptote, the thing they're asking me about. That plus as an exponent means from the right because it's positive. And so it's saying from here, look to the right, but now find where the graph is to the right, and now follow it backwards. Now, what is this graph doing? As I go backwards towards 3, but I'm on the right side of 3, I end up going down forever. And we have a mathematical symbol for down forever. It's negative infinity. So, hopefully, again, that clicks 3 from the right. Here's 3. There's the right of 3. Everywhere over here, but follow this graph segment back towards 3, and I end up going down forever, negative infinity. Okay, with that being said then, go ahead and take a second or two and look at negative 3 from the left. All right, if you need to write that down on the side, this is as x approaches negative 3 from the left, what will my graph do? And hopefully you can try to answer that one. Oh, you know what? Sorry, that's not negative 3, that's negative 2. Negative 2 from the left. I will correct your PDF. All right, as we approach negative 2 from the left, here's negative 2. Where's left of negative 2? Here it is. And what happens as I approach negative 2 from the left? I end up going up forever, which is positive infinity. All right, so again, where's your vertical asymptote here? Here it is at negative 2. I need to go to the left of negative 2, so over here, find the graph segment and follow it back towards the asymptote. I end up going up forever, positive infinity. All right, finally, what happens as x approaches infinity? Now this is different. The way you say this one is as x goes right forever. All right, so that's how you state that last one as x goes to the right forever, because after all, that's positive infinity. So what that means is look at the last thing you saw your graph doing as it started to trail off the page, and this started going like this. Now, what you need to ask yourself is this graph going to cross the x-axis or not? And what I would argue is, I'm seeing happen right here looks eerily similar to what I kind of saw over here. So I actually don't think, and I know I'm right on this, but I don't think this graph is going to end up crossing and continue to be positive. I think this is, in other words, behaving like a horizontal asymptote. So as this goes right forever, it's not going to cross and move up. It's actually going to more tightly hug, and that's another way of describing asymptote behavior. The graph will start to form and hug to this invisible line, but it will never cross it. Anyways, as I move right forever, I will start to hug and get very close to, but not cross, this horizontal line, which is the value 0. So you get close to 0, but you never actually touch or cross 0. Very interesting. All right, let's go ahead and take a look at the next one. Now I'm pre-reading to make sure I marked my asymptotes right this time, and I did. If I were you, I would maybe take this, pause it for a minute, and try these out. And I'm going to assume you did that. And here we go. So this one says negative 1 from the left. So where's my asymptote at negative 1? Here it is. From the left means I'm just somewhere over here, anywhere over here to the left of that asymptote, and I see this graph segment. Now that I've moved to the left onto this graph segment, I follow it back towards my asymptote, and as I do, my pencil starts going downwards very fast. So guess what? Downward very fast and forever is negative infinity. All right, this next one also says 4, but I guess here's the also, from the left. So where's 4? Here's 4. Where's from the left? Well, don't go too far this time because there's two different breaks. To the left of 4, I guess, puts me here in the middle between my two asymptotes. And as I follow this back towards 4, I end up going up forever, which is positive infinity. Now, this one is the only other one we haven't quite seen, but we pretty much have. This is saying as x goes left forever. And as x goes left forever, take a look. As I go left forever, the last segment is over here, and as I follow it left forever, I continue to get closer and hug this line. Where's this line? It is the y value, -3. All right. So be careful, careful. Make sure you really are careful about, like, yes, this is -1, but this means from the left. From the left, when you see that exponent as a negative. And if you see a positive in your exponent position, then that means from the right. And of course, x approaching positive infinity means going right forever off the page, and x approaching negative infinity means going left forever off the page. And you ask yourself, does it start to hug any horizontal line? And in this case, the horizontal line it was hugging was the x-axis itself, which would be the y value 0. This one was starting to hug the y value -3, so we specify the y value -3. All right. With that being said, I think that's a good stopping point for this video. Like I said, we're really flying over a bunch of concepts here, and so just be cautious of that.